Hello students. So today we are going to start redox reaction. Redox reaction is a very important topic of physical chemistry, and in IIT we find one question at least every year from this particular topic, and the questions of this topic can easily be answered if we develop some specific skill. This particular chapter requires a specific skill to attempt the problems of this chapter, and if gone that way, then it won't be difficult to answer the questions of this chapter. This chapter is, I call, a smart chapter, and it is always an asset of a good students, a good ranker. Good students always answer the question of this chapter definitely, because it is easier to answer, but not randomly. The questions, the topic must be done in a very systematic manner, but there are very few things in these chapters, so there are very few variables. If we master those variables, then we will be very comfortable in answering the question of this chapter. Moreover, this chapter has also involvement in other chapters of physical chemistry, like another very important chapter, which is electrochemistry, cannot be done without the knowledge of redox reaction. So redox reaction in itself is independent for one question, and it is a part of electrochemistry. Without knowing redox reaction well, electrochemistry cannot be done. Questions of electrochemistry cannot be done, because the chemical reactions involved in electrochemical process are all redox reaction. So there also we need a very thorough knowledge of redox reaction. So we are going to start today this very important chapter, redox reaction. In this chapter, we'll be doing the concepts in a very systematic manner. I will be starting from very fundamental parts of this chapter. Some of those things you may be knowing already, but I think they must be gone through systematically and sincerely once again from IIT point of view. So this is the first lecture of this redox reaction, in which we will be doing fundamentals of redox reaction. What is this redox reaction? What is the redox process? And what are the terminologies involved in the redox process? So the first thing comes in this chapter is the understanding of this term itself, which is redox. What do you mean by the term redox? Redox का मतलब क्या होता है? Redox term in fact is a combination of two terms. It is made up of two terms. They are reduction and oxidation. So red from reduction and ox from oxidation, and if you combine these two, it becomes redox. So redox reaction is in fact study of reduction and oxidation reaction. So in this chapter we are going to study the process of reduction and oxidation and the concepts involved in reduction and oxidation reaction. We'll be starting with definition of this redox reaction, reduction and oxidation reaction. Reduction and oxidation processes are defined several times. In the beginning, it was defined in a particular manner. Later, those definitions were found to be insufficient. Some of the reactions were not covered in those definitions, so later the definitions were modified and modified so many times, leading to the present day definition of redox reaction. So we will be starting from the classical definition of reduction and oxidation reaction, although those definitions are classical but not redundant even today, because those definitions are simple to understand and sometimes we can use those definitions, classical definitions, very easily in understanding the complicated redox reaction. So we will be starting from the classical old definition of reduction oxidation and slowly we'll develop the concepts of this topic. So first is, better we start from oxidation term first, although reduction comes first in the term redox, but better to start with oxidation first. Oxidation. Initially, it was defined as a process of addition of oxygen or a removal of hydrogen. So oxidation is a process of addition of oxygen or removal of hydrogen. Let us take few examples to exemplify this definition. If we write a reaction of carbon with oxygen giving CO2, it is oxidation of carbon. Oxygen is being added on carbon, so addition of oxygen. So we can say it is oxidation of carbon. Similarly, if we write CH4 plus oxygen giving CO2 plus water, again here we see oxygen is being added on methane. So methane is getting oxidized into carbon dioxide and water. So we can call it oxidation of methane. We can also take some more example. Iron plus oxygen giving Fe2O3. Here again oxygen is being added on iron, so it is oxidation of iron. So it is the process of addition of oxygen. Now take some example in which hydrogen is removed. If we take a reaction of ethane under certain circumstances, ethane can be dehydrogenated to ethene giving hydrogen gas. So it is a removal of hydrogen from ethane. We can call it oxidation of ethane. Similarly, if we write a reaction like if we heat calcium hydride, it gives calcium and hydrogen gas. Once again we can say it is oxidation of calcium hydride, removal of hydrogen. So oxidation of CaH2. So these are the few examples in which this definition apply appropriately. Oxidation, a process of addition of oxygen or a process of removal of hydrogen. In the first three reactions, oxygens are being added. In the last two reactions, hydrogen is being removed. All these are called oxidation. In the same manner, we define reduction reaction. Reduction is opposite to oxidation process. Reduction is just opposite in definition as well as in practice also. So, what is reduction? Reduction is process of addition of hydrogen or removal of oxygen. In oxidation, addition of oxygen and removal of hydrogen. In reduction, opposite, addition of hydrogen or removal of oxygen. So let us take few examples to explain this definition again. If we take an example of, say, ethene or ethyne, C2H2 is ethyne. If we add hydrogen, it is converted into ethane. So hydrogen is added on ethyne, it is reduction of ethyne. Similarly, if we take another example of, say, sulfur, when heated with hydrogen gives H2S. Hydrogen is added on sulfur, so reduction of sulfur due to addition of hydrogen. If you want to balance it, we'll have to write 8 here, so 8 is to S. So addition of hydrogen or removal of oxygen. If we write a reaction like this, SO3 on heating gives SO2 plus half O2. Oxygen is removed from SO3. So we can say it is a reduction of sulfur trioxide into sulfur dioxide. Reduction of SO3. We can take a few more examples, say Fe, or another better example way, heating copper oxide. If we heat copper oxide to very high temperature, it is converted into CuO, giving half O2. So it is removal of oxygen, reduction of cupric oxide, into cuprous oxide. So in this way, we define oxidation and reduction. They are the classical definition. Defined very first time what is oxidation and what is reduction process. But the limitation of this definition was that hydrogen or oxygen must be present in the reaction. Without presence of hydrogen or oxygen, with this definition, redox reaction cannot be explained. But there are so many reactions which are redox reaction but do not involve hydrogen or oxygen. So the redox reaction without hydrogen or oxygen involvement could not be explained with this example. So another definition was required, or we can say that modification of this definition was required. So to cover more redox reactions even without hydrogen and oxygen, redox reaction was redefined in this manner. So now we are moving to another definition of redox reaction, which is broader and cover more reactions besides covering the reactions of first definition. So second redox reaction was defined in terms of electron transfer. Redox reactions in electron transfer terms. If we consider a redox reaction, say sodium plus half Cl2 giving NaCl, it is a redox reaction. It is a redox reaction. But it cannot be explained with the help of first definition, because in this reaction there is neither hydrogen nor oxygen. This type of redox reactions can be explained with the help of the modified definition, which we are going to discuss now, redox reaction in terms of electron transfer. So according to this reaction, according to this definition, a redox reaction is an electron transfer process. A redox reaction is an electron transfer process. According to this definition, oxidation is a process. Oxidation is a process of loss of electrons. Oxidation is a process of loss of electrons, whereas reduction is a process of gain of electrons. Oxidation is a process of loss of electrons, a process in which electrons are lost is called oxidation, and a process in which electrons are gained are called reduction. Now, in light of this reaction, we know that here sodium is neutral atom and chlorine is a neutral molecule. But in sodium chloride, which is a salt, we have sodium as positively charged ion, cation, and chlorine as negatively charged chloride, anion. So in this reaction, sodium is converted into sodium ion and chlorine into chloride ion. How this may happen? If we write separately the conversion of sodium into sodium ion, it may happen only if sodium loses an electron. So in this reaction formation of sodium chloride from sodium and chlorine, sodium is losing an electron, and according to definition, oxidation is a process of loss of electron. So we can say that sodium is oxidized here because it is losing electron. Similarly, if we write conversion of chlorine into chloride, it may happen only if chlorine gain an electron. So we can say that chlorine is gaining electron, it is reduced to chloride. So chlorine is reduced. So in this process, in the formation of sodium chloride from sodium and chlorine, which is a redox reaction, we can say that sodium is oxidized to sodium ion and chlorine is reduced to chloride ion. So in fact, redox reaction is combination of two half reaction. Redox reaction is combination of two half reaction, oxidation half reaction and reduction half reaction. And if we combine them, if we algebraically add these two reactions, we obtain this redox reaction, sodium plus half Cl2 giving sodium ion, chloride ion, which is nothing but sodium chloride. So according to electron transfer process, oxidation is a process of loss of electron and reduction is a process of gain of electron. Redox reaction is a combination of two half reaction, oxidation half reaction and reduction half reaction. Moreover, these two half reaction must occur simultaneously. We cannot have this two half reactions separately independently. We cannot carry out oxidation today and leave reduction for tomorrow. These two reactions must be carried out simultaneously so that electrons produced in oxidation half reaction must be consumed in the reduction half reaction. Sodium is oxidized here because chlorine is there to accept that electron. If there is no chlorine for accepting this electron, sodium will not be oxidized. So redox reaction, oxidation and reduction reaction occur simultaneously and electrons produced in the oxidation half reaction are consumed simultaneously in the reduction half reaction. We can take one more example of this reaction. Suppose if we write a reaction leading to formation of another salt, say aluminum chloride. If we heat aluminum metal with chlorine gas, we obtain aluminum chloride. For the purpose of balancing, we can write 2, 3, 2. On left side, we have neutral aluminum, neutral chlorine molecule. But on the right side, we have salt, aluminum chloride. And in aluminum chloride, we know that aluminum has +3 valency and chlorine has -1 valency. So 3 chlorine -1 into 3 giving -3 charge, net 0 charge. How this is happening? if we again split this reaction, then we can say that aluminium is oxidized to Al3 plus, losing 3 electrons, and chlorine is getting reduced to chloride ion. Aluminium is oxidized, so it is oxidation, and chlorine is getting reduced, so it is reduction, half reaction. Now before we sum these two reactions, the electrons must be equal in these two reactions so that they cancel out after adding. For that purpose, we will have to multiply this reaction by 3, and then 3 electrons will cancel out 3 electrons, giving aluminium plus 3 by 2 Cl2, giving AlCl3, which is the required redox reaction. So in terms of electron transfer process, a redox reaction can more broadly be defined, and most of the redox reaction can be covered by this definition, whether it contains hydrogen or not, whether it contains oxygen or not. Next, we define two very important terms which we use frequently in this chapter, that is oxidizing and reducing agent. In short, we call it OA, and then we call it RA. So oxidizing and reducing agent. How we define these two terms? Oxidizing agent which oxidizes others. We have just discussed that these two reactions cannot occur in isolation. They must occur in conjugation. Electrons produced in one half reaction must be consumed in another half reaction. So for the reduction of chlorine, aluminium is responsible. Aluminium is producing electrons. So aluminium is agent for the reduction of chlorine, and we call it reducing agent. Aluminium is oxidized here due to chlorine. Aluminium is oxidized here due to chlorine. So oxidation of aluminium is due to the agent chlorine, and so chlorine is oxidizing agent. So oxidizing agent is a reagent. Oxidizing agent is a reagent which oxidizes others by reducing itself. Chlorine itself is getting reduced when it oxidizes aluminium. So oxidizing agent is the reagent which oxidizes others by reducing itself. Reducing agent is the reagent which reduces others by oxidizing itself. So in this reaction, aluminium is reducing agent because it is reducing chlorine by oxidizing itself, and and chlorine is oxidizing agent because it is responsible for the oxidation of aluminium, and itself chlorine is reduced. So oxidizing agent is reduced itself, reducing agent is oxidized itself. These two terms we will be using frequently in redox reaction. So this is another definition, a modification of the classical definition in which addition removal of hydrogen oxygen is used for defining redox reaction. However, even this definition is insufficient to describe clearly all the redox reaction. The redox reaction which we will encounter would be very complicated one, where it would be very difficult to detect, to identify which is losing electrons and which is gaining electrons. So, if we take an example for what we are talking about, say I am showing you just one simple redox reaction which we are going to encounter in this chapter. A reaction of potassium permanganate with potassium oxalate in presence of sulfuric acid to give K2SO4, MnSO4, SO4, CO2 and water. We can see how many reactants and products, 3 reactant, 4 products. It is a redox reaction, and truly speaking, it is a simple redox reaction. We will see much more complicated than this redox reaction, and in this redox reaction, it's very difficult but not impossible to find out which is losing electron, which is gaining electron, which is oxidizing agent and which is reducing agent. So for that purpose, oxidation and reduction reaction was further defined, further modified, and that will be the final definition of redox reaction which we will be using throughout this chapter. So let us move to the final definition of redox reaction which we will be using in this chapter. Redox reaction in terms of oxidation numbers. So now we are going to take the final definition of redox reaction which we would be using throughout this chapter, redox reaction in terms of oxidation number. Redox reaction can most conveniently be studied and manipulated in terms of oxidation number. But before we define redox reaction in terms of oxidation number, we must acquaint ourselves with the term oxidation number. Understanding of oxidation number in itself is a bit tricky. So let us first familiarize ourselves with oxidation number, and then we'll be back to redox reaction in terms of oxidation number. So now we are changing the heading, oxidation number, and then we'll be back to redox reaction in terms of oxidation number. So oxidation number concept which will be denoted by abbreviation ON. Sorry. Oxidation number. What is oxidation number? It must be understood very clearly. Oxidation number is the average charge. Oxidation number is the average charge possessed by an element, not atom only. It is the average charge possessed by an element in a given compound or an ion. So let us define it. It is the average charge possessed by an element in a given compound or ion. In a given compound or ion. Then how we determine this? How we find out this? There are certain rules we follow in determining the oxidation number, average charge on an element in a given compound. And those rules must be strictly followed in determining the oxidation number of an element in a compound or ion. So we are going to lay down those rules and then we will be applying those rules in finding some oxidation number, and then we will be back to definition of redox reaction in terms of oxidation number. The first rule related to oxidation number is oxidation number of an atom in elemental state is always 0. Let us write it first. Oxidation number of an atom in elemental state is always 0. What it means? If we talk of sodium, potassium, calcium on any metals, we know that in elemental state they all exist as monoatomic atom. So if in a reaction we have sodium or we have calcium or we have iron, oxidation number of all this will be 0. If they are in the free atomic state. Elemental state, the state in which element exists at room temperature. If we talk of oxygen, it exists in form of O2 at room temperature. If we talk of nitrogen, it exists as N2. If we talk of chlorine, it exists as Cl2. If we talk of phosphorus, white phosphorus is P4. If we talk of sulfur, rhombic sulfur is S8. So they are the elemental state of elements, and in these states oxidation number of oxygen is 0, nitrogen is 0, chlorine atom is 0, phosphorus atom is 0, sulfur atom is 0. That means we'll take average charge on each sulfur in acid 0, phosphorus 0, chlorine 0, nitrogen 0, oxygen 0. So oxidation number of element atom in elemental state is always 0. This is the first rule. Then comes the second rule. Oxidation number of alkali metal in compounds is +1 and it never changes. That means oxidation number of lithium, sodium, potassium, rubidium, cesium in all its compound is always +1. Oxidation number of alkali metals in all its compound is always +1. In NaCl, sodium is in +1 oxidation state. In K2SO4, potassium is in +1 oxidation state. In sodium phosphate, sodium is in +1 oxidation state. It never changes. Similarly, oxidation number of alkaline earth metals in all its compounds is always +2. Like in calcium chloride, calcium is in +2. In barium sulfate, oxidation number of barium is +2, and in magnesium phosphate, magnesium is in +2 oxidation state. Means charge on one magnesium is +2. Here we have 3 magnesium, so total charge will be +6. Oxidation number of aluminium in all its compound is always +3. So whether we take AlCl3 or Al2SO4 whole 3, it is always +3. So oxidation number of aluminium is always +3. Third, oxidation number of hydrogen. In a compound, hydrogen can be bonded to metal or non-metal. If hydrogen is bonded to non-metals, its oxidation number is always +1. Oxidation number of hydrogen in all its compounds where it is bonded to non-metals is always +1. Like if we take CH4, hydrogen is +1. If we take H2S, hydrogen is +1. If we take PH3, hydrogen is +1. And if hydrogen is bonded to metal, that is called metal hydride, then oxidation number of hydrogen would be -1. So oxidation number of hydrogen in metal hydride is -1. Like In sodium hydride it is -1. In calcium hydride it is -1. In aluminum hydride it is -1. So oxidation number of hydrogens are assigned in this manner. Next, in oxidation number rule, we move to oxygen, which is very important. Oxidation number of oxygen must be assigned with special precaution, and oxygen is very common element we find everywhere. So let us see the rules for assigning oxidation number of oxygen. So rule number 4, oxidation number of oxygen in all its compounds is always -2. Like if we take CO2, oxygen has -2 oxidation number. If we take H2O, oxygen has -2 oxidation number. If we take Fe2O3, oxygen has -2 oxidation number. But there are some exceptions to this. In peroxide, oxidation number of oxygen is -1. In peroxide, oxidation number of oxygen is -1. H2O2, we are all aware of this compound. This compound is called hydrogen peroxide. So here, oxidation number of oxygen is -1. Similarly, if we have CaO2, it is calcium peroxide, oxidation number of oxygen is -1. There are compounds called superoxide. In superoxide, oxidation number of oxygen is -1/2. KO2 is potassium superoxide, where oxygen has -1/2 oxidation number. So oxidation number of superoxide, oxygen in superoxide is -1/2. There is a compound, oxygen fluoride. In OF2, oxidation number of oxygen is +2. This is the only compound in which oxygen exists in +2 oxidation state. As we have said earlier, that oxidation number is the charge. And in a compound, charge is decided on the basis of electronegativity. More electronegative atom possesses negative charge, and less electronegative atom possesses positive charge. And we all know fluorine is most electronegative atom, so negative charge is always present on fluorine. Negative charge is always present on fluorine, and oxygen is next to fluorine. So oxygen usually remain in negative oxidation state, but if bonded to fluorine, which is more electronegative than oxygen, oxygen acquire positive charge and its oxidation number will be +2. So that is about oxygen. Then comes Fifth rule, oxidation number of halogen in metal halides is always -1. But be very careful in assigning oxidation number of halogen. We have written here metal halides means if halogen is bonded to metals only, nothing else. Here we can see the term metal halides. If we have compounds like FeCl3, then we can say that it is metal and halogen, so metal halides. Chlorine is -1. If we have zinc bromide, metal halogen, metal halides -1. But if we have NaClO3, it is not -1. Halogen is not bonded to metal. It is not metal halides. It is basically sodium chlorate. So oxidation number of halogen is not always -1. But if halogen is bonded to metal only, then we can say that its oxidation number will be -1. Oxidation number of sulfur in metal sulfide is always -2. If we have Na2S, CaS, FeS, then we say that they are metal halides, metal sulfides, and sulfur is in -2 oxidation state. But the condition again is that there should be only metal and sulfur. If there is any non-metal, then sulfur will not be in -2 oxidation state. Then comes the next and the last rule in this regard. Oxidation number of an ion is always equal to the charge on ion. Is always equal to the charge on ion. Ion can be monoatomic, ion can be polyatomic. If we have Cl minus, then we say that oxidation number is -1. If we have sulfate ion, we can say oxidation number of sulfate as a whole. We'll be using this. That oxidation number is what? Average charge. So if there is one sulfate and total negative charge is -2, we say that oxidation number of sulfate is -2. So sulfate is -2. Similarly, if we have phosphate, we say that oxidation number of phosphate is -3. Another very common ion we will encounter in this chapter is oxalate, whose oxidation number is -2. So oxidation number of ion is always the charge on that ions. So with the help of these rules, we determine oxidation number of unknown element in a given compound or ion. Let us now use these rules to determine oxidation number of elements in some of the commonly encountered oxidizing reducing agents. So now we are going to apply these rules to determine oxidation number of unknown elements in a compound or ions. If we take a very common compound we will encounter in this chapter, potassium permanganate, and we want to know oxidation number of potassium, oxidation number of manganese. Then oxidation number of potassium and oxygen are known according to rule. If we assign oxidation number of manganese to be X, potassium is +1, oxygen is -2, and total charge on KMnO4 is 0, it's a neutral compound. So we will say that oxidation number of potassium permanganate is 0. So +1 potassium plus X manganese, a -8, -2 into 4 oxygen is equal to 0. So X comes out to be +7, and we say that oxidation number of manganese in this compound is +7. Another common example is K2Cr2O7, which is called potassium dichromate. Here again, chromium is unknown element. Let us assume oxidation number of chromium to be X. So for 2 potassium we'll have +2 +1 into 2. For 2 chromium 2X. For 7 oxygen 7 into -2. -14 will be 0. If we solve it, it is +6. So we say that in this compound oxidation number of chromium is +6. Means average charge on 1 chromium is +6. Total charge on 2 chromium is +12, so average charge is +6. But we are not giving guarantee that the exact charge on both chromium is +6 each. It is just a mathematical term which is average charge, not the exact charge. If we take compound KNO3 and we want to know the oxidation number on nitrogen, again X, so +1 on potassium, X on nitrogen, and 3 oxygen -6 is equal to 0, so X will be +5. We say that nitrogen is in +5 oxidation state. If we take a compound Na2S2O3, again sodium oxygens are known. So if we take sulfur X, for 2 sodium +2, for 2 sulfur 2X, for 3 oxygen -6, and that will be 0. So X will be equal to -6 + 2, -4 on right side, +4 divided by 2 +2, so sulfur is in +2 oxidation state. Similarly, if we take some ions, say CrO4 2- ions. If we take oxidation number of chromium X, so X 4 oxygen 4 into -2 -8, will now be equal to -2, which is oxidation number of chromate. So if we solve it, X comes out to be 6. And we again say that chromium is in +6 oxidation state. If we take K2C2O4, potassium oxalate, if we assume oxidation number of carbon to be X, for 2 potassium plus 2 carbon, 2X, 4 oxygen, -8, 4 into -2, -8. And that will be 0. So X will be +3, -8 plus 2, -6, on the right side +6 divided by 2, +3. So we say that carbon is in +3 oxidation state. Carbon is in +3 oxidation state. So in this manner, we determine oxidation number of unknown element using the oxidation number of known elements in a given compound or ion. Now we will be back to a redox reaction, and we will be defining a redox reaction in terms of this oxidation numbers. So let us move to the final definition of redox reaction in terms of oxidation number. How we define a redox reaction in terms of oxidation number. A redox reaction, reactions in terms of oxidation number. In terms of oxidation number, we define oxidation. Oxidation is a process of increase in oxidation number. Oxidation is a process of increase in oxidation number. Process of increase in oxidation number. And the reagent which undergo increase in oxidation number will be called oxidized. The reagent undergoing increase in oxidation number is oxidized, and the one which is oxidized act as a reducing agent. Act as a reducing agent because itself is oxidized, so it will reduce other. So acts as reducing agent. So one which undergo increase in oxidation number is oxidized, act as a reducing agent. Then what is reduction? Just opposite to this. Reduction, a process of decrease in oxidation decrease in oxidation number. See, process of increase in oxidation number is oxidation and decrease in oxidation number is reduction. Reagent undergoing decrease in oxidation number is reduced, and the one which is reduced itself, जो खुद reduce होगा, will oxidize other, so will act as an oxidizing agent. Acts as an oxidizing agent. So reagent undergoing decrease in oxidation number is reduced and act as an oxidizing agent. So let us apply this two definition of redox process in identifying the reagent undergoing oxidation and reduction in the actual redox reaction which we are supposed to encounter in this chapter. So we are going to identify the reagent getting oxidized and reduced and oxidizing reducing agent. If we take an example of a very common redox reaction which I have written earlier also, a reaction of potassium permanganate with K2C2O4 in presence of H2SO4 giving MnSO4 plus CO2 plus K2SO4 plus H2O. Now our task is to identify in this redox reaction which is oxidized, which is reduced, which is oxidizing agent and which is reducing agent. So we'll check the oxidation number, which element is undergoing increase in oxidation number and which element is undergoing decrease in oxidation number. In this reaction, there are some elements whose oxidation numbers never changes. So there is no need to check those elements. In this reaction, potassium is on both sides and we know that oxidation number of potassium never changes, it is always +1. Similarly, oxidation number of oxygen in ordinary compounds, normal compounds, is always -2, so that can also be left. So we have left potassium, oxygen, hydrogen in ordinary compound is always +1, so also there is no need to check hydrogen. Sulfur is in the form of sulfate and sulfate is same everywhere. Here we have sulfate, sulfate, sulfate. So again there is no change in oxidation number of sulfate, so there is no need to check sulfur and sulfate. So the left elements only are manganese and carbon. In this KMnO4, if we determine the oxidation number of manganese, we find for potassium +1, oxygen -2 into 4, -8. Net charge is 0, so -8 or +1, -7, so manganese must be +7, which will make the total 0. So manganese must be +7. So plus 7 plus 1 plus 8 minus 8, 0. Here on potassium there is plus 2, 2 potassium, 4 oxygen, minus 8. So on 2 carbon we have plus 6. On 2 carbon plus 6, minus 8 or plus 2, minus 6 or plus 6 on 2 carbon. So plus 6 on 2 carbon. Oxidation number is average charge, so it must be plus 6 by 2 plus 3. Carbon is in plus 3 oxidation number. On the right side, the sulfate has minus 2 oxidation number, so manganese plus 2. 1 carbon is minus 2, so 2 carbon minus 4. So carbon is plus 4 and manganese is plus 2. Now we can see the only elements undergoing change in oxidation number are manganese and carbon. Manganese is undergoing decrease in oxidation number, plus 7 to plus 2. So we can say that potassium permanganate is being reduced. Reduction is occurring for potassium permanganate. Reduced, plus 7 to plus 2. And the one which is reduced oxidizes other, and therefore in this reaction it is acting as an oxidizing agent. Potassium oxalate undergoing increase in oxidation number, plus 3 to plus 4. So it is oxidized and the one which is oxidized reduces other and act as a reducing agent. So we have applied oxidation number to describe this redox reaction. That in this redox reaction, potassium permanganate is oxidizing agent undergoing decrease in oxidation number, undergoing reduction, and potassium oxalate is reducing agent undergoing increase in oxidation number. So now we are going to see a lot of redox reaction in which we'll apply this to identify oxidizing reducing agent. That is the first step of this redox reaction, and here we start the substantial discussion of redox reaction. Till now we have discussed the fundamentals of redox reaction. Now if we take an example of K2Cr2O7 plus Ki plus K2 plus H2SO4 given K2SO4 plus Cr2SO4 whole 3 plus iodine plus H2O. Now again we will not check potassium, oxygen, sulfate, hydrogen. So if we leave them, we are left with chromium and iodine. They are the two elements which needs to be checked. Here potassium plus 2 on 2 potassium, minus 14 on 7 oxygen, 7 into minus 2. So minus 14 plus 2, minus 12, so plus 12, plus 12, but on 2 chromium, So oxidation number is average charge, it is +6. Potassium in Ki is +1, so iodine is -1. On the right side we have in chromium sulfate 3 sulfates, so -6, so +6. But on 2 chromium, so oxidation number, average charge +3. Iodine is in elemental state, so 0. So potassium dichromate undergoing decrease in oxidation number. It is reduced and therefore oxidizing agent. Potassium iodide undergoing increase in oxidation number -1 to 0, so oxidized, reducing agent. Some more examples. Suppose if we have KMnO4 plus CH3CHO plus KOH giving MnO2 plus CH3COOK plus H2O. Now, in manganese, now we can easily determine the oxidation number of manganese. +7, +1 -8, -7, so +7. In this compound, CH3CHO acetaldehyde, we have 4 hydrogen, 3 here, 1 here, 4 hydrogen. So +4 on hydrogen, -2 on oxygen, so net is +2. So on 2 carbon, -2. 2 carbon. So each carbon is -1. So in this compound, oxidation number of carbon is -1. On the right side, oxygen is -2, so 2 oxygen -4, so manganese is +4. In this compound, we have 3 hydrogen, so 3 hydrogen is +3, 1 potassium is +1, 2 oxygen is -4, so net is 0. So carbon is in 0 oxidation number. Now see, potassium permanganate is undergoing reduction 7 to 4. Reduced. So it is oxidizing agent. Acetaldehyde -1 to 0 oxidized. So reducing agent, it is reducing agent. So now we can understand very clearly what is happening here, how we are determining all this. They are the very strong tools of redox reaction, and you will wonder to know that students struggles here only. If you do not find out oxidation number appropriately, you will end up with a wrong stoichiometry of the redox reaction. Some more example. Suppose we have a reaction KMnO4 plus Na2S plus H2SO4 giving K2SO4 plus MnSO4 K2SO4 plus MnSO4 plus Na2SO4 plus H2O. Now we can see manganese here is in +7 oxidation state. Sulfur in this compound is in -2 oxidation state. We have sulfur in H2SO4 also. On right side we have sulfur in the form of sulfate only, sulfate. So we can say that this sulfur has also gone into sulfate. So on right side the total sulfate consists of some sulfates from H2SO4 and some sulfates from sodium sulfide. And in sulfate the oxidation number of sulfur is +6. For oxygen -8 +2 -6, so +6. So we can say that sulfur is oxidized from -2 to +6. Manganese is in +2 oxidation state here. So manganese is reduced. So potassium permanganate is oxidizing agent because it is undergoing reduction, and sodium sulfide is reducing agent because it is undergoing oxidation. One more example. Let us take NaIO3 plus H2O2 in H2SO4. Now, if we write on the other side Na2SO4 plus iodine plus H2O plus O2. On left side, if we determine oxidation number of iodine, it will come out to be +5. 3 oxygen -6, -6, 1 sodium +1. So -6 plus 1 plus -6 plus 1 -5, so +5. It is hydrogen peroxide. So oxygen here is in -1 oxidation state. 2 hydrogen plus 2, so -2 and 2 oxygen, peroxide -1. On the right side, iodine elemental state 0, and the oxygen from H2O2 has gone to O2 where it is 0. Sodium iodate is reduced +5 to 0, so it is oxidizing agent. But H2O2 is oxidized, so it is a reducing agent. So in this manner, we identify oxidizing reducing agent in common ordinary redox reaction. Now let us take an example of a slightly different type of redox reaction. Let us take an example of a redox reaction Br2NaOH giving NaBr plus NaBrO3 plus H2O. If we see on the left side, bromine is in zero oxidation state. But on the right side, we have bromine in -1. Here bromine is +5. Here we have just one reagent, bromine, which is simultaneously undergoing reduction 0 to -1 reduction, and the same is undergoing oxidation also 0 to +5. It is oxidation also. Here the same reagent is undergoing reduction as well as oxidation. It is possible. It is a redox reaction. And this special type of redox reaction has been given a specific name called disproportionation. Disproportionation reaction. But it must be understood very clearly. Disproportionation redox reaction are those redox reactions in which same reagent is oxidized as well as reduced. Same reagent is oxidized as well as reduced simultaneously. Same reagent is oxidized as well as reduced simultaneously. If we write a reaction, which always confuses us whether it is redox or not, if we write a reaction NaI plus NaIO3 plus H2SO4 giving I2 plus Na2SO4 plus H2O. If we see this reaction, on left side we have iodine in -1, iodine in +5, on the right side iodine is in zero oxidation state. Iodine is oxidized from -1 to 0, iodine is reduced from +5 to 0. Same atom is oxidized, reduced, but it is not a disproportionation reaction. The reagents are different. These two are different reagent, and therefore it is not a disproportionation. It's not a disproportionation reaction. However, in IITJ there was a question that which of the reaction is disproportionation in reverse direction. Then it will become the answer. If we see from reverse side, from right to left, then we can say that iodine is oxidized, iodine is reduced, same reagent is oxidized, reduced, so it is disproportionation in reverse direction, but not disproportionation as written. We can see some more example of disproportionation reaction. If we write a reaction P4 NaOH, giving pH 3 plus NaH2PO2. Phosphorus here is 0, here is -3, here it is +1. So 0, -3 reduction, 0 +1 oxidation, it is disproportionation. If we write S8 plus NaOH giving Na2S plus Na2SO3, 0, -2 plus 4, -6 plus 2, -4, so plus 4. 0 to -2 reduction, 0 to +4 oxidation. H2CO plus NaOH gives CH3OH plus HCOONA. In this compound, carbon is in 0 oxidation state, +2 -2 0. Here we have 4 hydrogen +4, 1 oxygen -2, so +4 -2 +2, so carbon is in -2 oxidation state. Here we have 2 oxygen -4, hydrogen +1, sodium +1, so +1 +1 +2, -4 -2, so carbon is +2. 0 to -2 reduction, 0 to +2 oxidation, same reagent, formaldehyde is reduced, oxidized, it is disproportionation. We can see one more example. Cu2O H2SO4 giving CuSO4 plus Cu plus H2O. Copper here is +1, oxygen -2, so +2 on 2 copper, 1 on 1 copper, +1. Here is +2 oxidation, 0 reduction. So this way we describe this type of redox reaction, which is called disproportionation. Then one more type of redox reaction we can see. Let us see FeC2O4 KMNO4 plus H2SO4 gives Fe2SO4 whole 3 MnSO4 K2SO4 CO2 H2O. If we check for the element undergoing change in oxidation number, on left side we have iron oxalate. So oxalate as a whole is -2, so iron here is +2. On the right side iron is +3, so iron is undergoing oxidation. At the same time, if we find out the oxidation number of carbon in oxalate, we find out +3, we find it out +3. Oxalate को separately हमने किया है, आप फिर से देख सकते हैं. So we find oxidation number of carbon in oxalate +3. On the right side, carbon is +4. Manganese here is +7. On this side it is +2. What we can see now, two elements, iron and carbon, are undergoing oxidation. +2 to +3 oxidation of iron, +3 to +4 oxidation of carbon, and manganese is undergoing reduction. It is possible that in a redox reaction more than one elements are oxidized simultaneously. and more than one elements are reduced simultaneously. In the next lecture, we'll start balancing of redox reaction. All this would be very important, and the balancing of redox reaction would first depends on identifying the oxidizing reducing agent element undergoing change in oxidation number. So here it is a case of redox reaction in which more than one atoms are oxidized, reduced simultaneously. We can see one or two more examples. If we write FeNO2 whole 2, K2Cr2O7, H2SO4, it gives Fe2SO4 whole 3, KNO3, K2SO4, Cr2SO4 whole 3 plus water. It is ferrous nitrate. So here we have iron in +2. In nitrite, ferrous nitrite, in nitrite, nitrogen is in +3 oxidation state. We can see it separately. NO2 minus. So X minus 4 is -1, X minus 4 is -1. So X is +3. In dichromate we have seen chromium +6. Here iron is +3. Nitrogen is +5 in nitrate and chromium is +3. Both iron and nitrogen are getting oxidized and chromium is getting reduced. One more example. Cu2s, KMnO4, H2SO4 giving CuSO4, MnSO4, K2SO4, SO2, H2O. Metal sulfide, sulfur is -2. So +2 on 2 copper, so copper is +1. Manganese +7. The sulfur of cuprous sulfide is here +4. Copper is here +2. Manganese +2. Copper is oxidized from +1 to +2. Sulfur is oxidized from -2 to +4. Manganese +7 to +2. So more than one elements are oxidized. So here we conclude the first lecture of redox reaction, in which we have developed fundamentals of redox reaction. Now we can identify in a given redox reaction which is undergoing reduction, which is undergoing oxidation. Then only we can proceed further. So in the next lecture we'll be taking balancing of redox reaction. We'll try to balance all this type of redox reaction, and there are certain specific techniques of balancing of redox reaction. This type of redox reaction cannot be balanced by hit and try. This can be balanced only through certain techniques. There are certain standard methods. We'll discuss those methods first, and then at the end I will let you know an expert method using which you can balance any of this redox reaction just in less than a minute, and I can say in the blink of an eye you can balance any of the redox reaction.